Hello and welcome to another class of ATMO 620. I hope you're all doing well, and I hope you're enjoying the topics that we've covered so far. Just as a reminder of where we are right now, we started this class talking about some basic thermodynamics. We then discussed the thermodynamics of moist air and what happens when you include water vapor into the picture. And then we started talking about processes that that can lead to the formation of clouds. So condensation of water vapor, formation of liquid droplets. We talked about various mechanisms for the formation of the liquid droplets. Then we talked about ice and ice crystals. Today we want to continue on this journey discussing cloud microphysics, and a journey that we're almost at the end of. And today we will talk about rain and snow, okay, and some processes that affect rain and snow, and some properties of rain and snow that are useful to know. So today's topic is mostly about precipitation as opposed to just what happens when you when you nucleate crystals or liquid droplets. Okay, so the main quantity, or one of the most important things when we think about precipitation in general, one of the most important properties that we care about is the so-called drop size distribution, or the spectrum, if you will. Most of precipitation, as we said a few classes ago, most of precip that falls on the surface reaches the surface as in the form of rain. And typically we use a quantity called precipitation rate to quantify how much it is raining in a particular area, okay? And this gives you some idea about the intensity of the rainfall, which indirectly tells you something about the intensity of the processes that led to the formation of the rain. Second in importance to the precipitation rate is the drop size distribution. This tells us something about the environment, about the conditions in which rain was formed, and something about the processes that happened to the raindrops, perhaps, as they fell towards the surface. Now, in this context, one of the first pieces of work that were produced in the years were due to two scientists called Marshall and Polymer, and essentially they found that the distribution, the drop size distribution, is a function of diameter, essentially behaved as an exponential. Okay, this is the form here. Let me this pencil. So n0 is some kind of constant, and e to the lambda d is what describes the exponential behavior. Lambda, of course, has the units of 1 over meters or 1 over millimeters, according to how you measure the diameter. This here is a representation of these curves, okay? And these are curves for a different, let's say for different n0, for different precipitation rate, okay? These are, I think these are measured, yes. These are actually measured from observations, okay? Notice that after about 1 millimeter, 1.5 millimeter, let me explain. The continuous line is the theoretical values that you expect from the Marshall-Polymer distribution, and the x-axis and the y-axis is the n of d in logarithmic scale, and x-axis is simply the diameter. Notice that these are perfect lines, whereas this is an exponential. How can that be? Where we're looking at the logarithmic scale over here. So an exponential logarithmic scale is just a linear function, right? So it kind of makes sense. And if you're dealing with exponential, it's easier to use a logarithmic scale. If you're dealing with power laws, it's better to use a double logarithm that will show the linear nature of what you're looking at. After about 1.5 millimeter, notice that the observed behavior is actually follows quite well the line. Okay, so these are fairly good descriptions for large enough radii, if you will. But at small diameters, this is not the case. Okay. Yes. Okay. Now, why do we observe a behavior like that, right? Why do we have an exponential behavior? Well, and in particular, why does the drop spectrum decreases at large radii, right? Why isn't it a constant or whatnot? That kind of has to do with the fact that droplets, really, really small droplets, if you remember, we talked about really strong surface tensions, and so you could think of them really as hard balls. But when the droplets become really, really big, then the surface tension is sort of less important, if you will, and so the droplets can get kind of deformed. Okay, and in particular, this deformation causes what we call drop breakup. Okay, so the droplets literally break up. Okay, in particular, we'll talk about this a little bit more, but this is a comparison between some theoretical this shows the deformation essentially of droplets for droplets of different diameters. The lines show the theoretical values that you'd expect, and the dots of various shapes are the observed values in different experiments. Okay, so we don't really care. We don't really need to go into the details. The axis ratio means the deformation essentially. So if you have a drop, you could define an axis A and an axis B. Okay. When A equals B, then this is not the droplet is not deformed essentially, and this has a spherical shape, and this tends to be the case for particularly small droplets. But for very large droplets, notice that this deformation ratio is about 0.5. Okay, meaning that the droplets actually have a more squeezed form. This deformation ratio, there's ways to derive some kind of an empirical theoretical formula as a power law, that kind of interpolates this behavior. It's not necessarily important that you memorize this, but just keep in mind that as the droplets get bigger and bigger, they get deformed. Okay. And when the droplets are large enough, okay, so when they have a pretty large deformation when they're large enough, they have a large deformation ratio, and also essentially they oscillate. Okay, you could think of them as essentially membranes of a drum. Okay, the drum is kind of the membrane of the drum. If we look at it from above, is kind of held on some fixed points, right, on the drum, and it's made really, really tight. And thanks to this tightness, we're looking at it from above, the membrane can oscillate, right? This is seen sideways. Suppose you have your drum. The skin on top is kind of held really tightly to the drum, and this makes it oscillate. If you will, for the droplet, what keeps the droplet surface tight is surface tension, right? Any point is attracted by its neighbors, and the droplet kind of closes on itself, right? And because of that, you can you can excite oscillations on the droplet. Now, where's the trick? For really small droplets, the oscillations have very, very large frequency. Okay, so these oscillate at very large frequencies. For larger droplets, the frequency is much, much lower. Okay. And, so you could imagine at a lower frequency, you could imagine really these oscillation modes affecting the shape of the droplet. Whereas if you had one tiny droplet, let's say that, you zoom in, if you had a really, really high frequency, it would look like something like this, right? Where you would have a lot of vibrations along this line. But if you had a lower frequency, instead of having this, if you had a lower frequency, you could have a much more important deformation of the droplet. Okay, and this is important because oscillations also, by the way, can be excited. If you're wondering, so what if there can be oscillations? Well, whenever you have collisions or anything that hits, even if it's a collision without a coalescence, those can excite. Excite the droplets. Well, so what if droplets can oscillate? Well, the oscillation of droplets is important because this can create even more deformations of the droplet. Okay. The graph here shows what might happen, for example, to a droplet, right? So you have a large droplet that's falling at a certain speed, and that already you see is deformed. It could happen that if the droplet is large enough, this deformation actually becomes kind of unstable and leads to this very tiny filament, which then leads to a breakup. Okay. Oscillations, oscillations can certainly facilitate this breakup, because maybe they stress this filament, or maybe they stress one of these structures and facilitate the creation of this tiny little filament. And so when you have really, really large droplets, it is more likely that these droplets can become unstable and break down or break up. And so that's why the spectrum goes like e to the minus the radius or the diameter of the droplet, because at a certain point you become unstable. With some kind of empirical approach, you can actually determine what is the diameter, the maximum diameter of a droplet past which you actually become unstable and you break. Okay, you break the droplet. And you can also, So remember this formula. This is not particularly important. You can also estimate the probability of a breakup given the drop radius and given some coefficient. Okay, this is a little bit empirical and hand waving, but it's also not particularly important. Another thing that we discussed that could facilitate the breakup, this is something that we discussed a while ago, is the possibility of having collisions. So instabilities, aerodynamical instabilities, and things due to aerodynamical instabilities and things due to oscillations, that's one thing, but also collisions. Suppose you have a larger droplet, that is now kind of deformed, and that is falling down. This is the droplet falling down. imagine that this is falling at a greater speed than a droplet that is down here, or maybe a droplet that is down here. And so at some point, this droplet will hit, depending on the difference in velocity. If we were on a reference frame that is following this, it would be like having this projectile shot against this, and this may result in the breakup of this droplet into two smaller droplets. Okay, and it's kind of possible to determine the efficiency of this. I think this is something that we covered a while ago. We talked about the probability of having coalescence, or the efficiency of coalescence, was something that was somehow minimized for the radius of the smaller droplet equal to half roughly of the radius of the bigger droplet. This is a way to quantify this empirically, and you can estimate the coalescence efficiency in this way, where F is some factor that depends on the ratio of the two of the radii of the two droplets, and minima have been found actually for droplets that are 0.6 of the radius of the smaller droplets that are 0.6 of the radius of the larger droplet. So yeah, just keep in mind another way that breakup could happen is because of collision processes. That's certainly a possibility. The challenge when you consider drop breakup, and particularly breakup due to the collision between two droplets, is that you start off with a droplet of volume V1 and another droplet of volume V2. The first challenge is to know what happens, like how many droplets are you going to end up having. The second challenge is what is V1 prime, V2 prime, ... Vn prime. So what is the volume of the resulting droplets? We're talking droplets here, so volume and radius is kind of the same thing in a way. And it's been found sort of experimentally that a reasonable approximation is that each collision induced breakup produces exactly 3 satellite drops, and these kind of miraculously have equal volume. Okay, and this volume is given by this, these are all equal to V prime. You can call it V prime here. This is equal to this. Okay. Okay, and again, this would be something very hard to determine, sort of theoretically, and so these are mostly determinations that are done kind of experimentally or with a heuristic formula and whatnot. Okay, so keep in mind that, these are all either from observations or like from very, very, with a lot of approximations. Okay, so how do sort of breakups happen? What I showed before were results from a study by Brazier-Smith et al. And this is from the 70s. Okay, this was a study that was done in the labs. And this was criticized later on. And it was criticized because, and this is one limitation of using the lab, because Brazier-Smith et al. Used, first of all, collisions at an angle rather than head-on collisions. And then the effect of air was kind of neglected. So the effect of having turbulence, turbulent currents going on was kind of neglected, okay? So first, collisions are at an angle, and second, the effect of air was neglected. It turned out that if you did the experiment in a more sophisticated form, For example, here I'm reporting low enlist, from a study in the 80s. Well, in this case, different ways of sort of breakup patterns were found. And one form of breakup was called a neck breakup, where you have the droplet, and for some reason, maybe due to turbulence, maybe due to, I don't know, collision with another particle, maybe due to oscillations even, right? Suppose that you have a droplet that is kind of deformed, and suppose that, some oscillation is going through this droplet. You may end up with a situation where, let's say that this and this is an oscillation, you may end up with something like this for whatever reason. This creates a little neck here that becomes then elongated. And this is really just a tiny filament. And again, because these droplets are falling at a relatively great speed, the air might help making this even more unstable. You could have a sheet instability or a sheet breakup, which is kind of similar to the neck breakup, but instead of having a structure like this, you really have something like this, where you have like a small sheet and the droplet here, and this also might become detached. You could have that the droplet becomes so deformed and becomes similar to a disk, and this is so thin that at some point it just explodes, and it explodes in smaller droplets like this. Or you could have, they call a bag instability, where this even, not only is it flat, but it has like kind of a concave, it can have like a concave shape or a weirdly elongated shape of some form like this. And this then, again, explodes and results in multiple drops. So, as this suggests, the problem of breakup of droplets is actually extremely complicated. It's actually extremely complex, and not easily tractable, because, suppose you have a disk. Again, in how many particles does this disk break into? What are their sizes and whatnot? So it is a complicated. It is a complicated process. Clearly, when you have two drops colliding, the point of impact between the two drops is obviously an important parameter, right? Because if they collide head-on, or if they collide sideways, suppose they're traveling in opposite directions, okay, for simplicity. These are going to have different effect, right? Where this will be a massive collision. This might actually not result in any kind of coalescence, and it just maybe trigger some oscillations, but may not have a bigger effect on the droplets. But the point of impact is one part of the story, but not the only part of the story. Another important parameter is the kinetic energy that is sort of that is what's the word I'm looking for? The kinetic energy that is involved in the collision, if you will. Okay, this is another important quantity. And in particular, you can derive this formula, but it's not important to do it now. We can define a quantity called collision kinetic energy, which is defined in this way. It looks kind of complicated, but it really isn't. U is the relative velocity between the two particles. Big R and small r are the radii of the two particles, and gamma is the ratio between the two. Rho of L is the density of liquid water. Okay. Now, the collision kinetic energy, as you might expect, as it's kind of reasonable to expect, collision kinetic energy is it affects the type of collision and a type of breakup that you're going to have. Okay. And in particular, remember the different breakup modes that that I showed you before, for really, really high collision kinetic energies, basically all modes of breakup can happen, okay, depending obviously on point of contact, okay, between two particles. When you have smaller collision kinetic energy and smaller gamma, meaning that one droplet is much, much bigger than the other, then filament breakup is more likely regardless of the point of contact. And for really, really small kinetic energy, then there can be coalescence, okay, provided that the total energy is dissipated through oscillations and deformation of the drop, meaning that in this case, you'd have one droplet and you'd have the other droplet, and they will be approaching really, really slowly, okay? And once they approach, obviously, it's like when you hit your car against something, this kinetic energy that existed before has to be transformed in something, right? And it can be dissipated through oscillations within the new thing that is formed. And oscillations may kind of dissipate this extra energy, and so then you have formed a new droplet. What happens if the kinetic energy is too much? Well, if the kinetic energy is too much, you might still form a larger droplet, and the droplet might still be trying to get rid of the extra energy through oscillations, but these oscillations might actually be really, really big. And if these oscillations are very energetic, these might deform the droplet a lot, right? I don't know what I try to do here, but what I meant to say is that these oscillations might deform the droplet a lot. And because of this, you may make it easier for the droplet to break up in various different ways, okay? So these two parameters are kind of important. These are just plots that illustrate the probability of having a particular kind of, the size distribution of the fragments that are produced by different kinds of breakups. Okay, so you have filament, the sheet, and the disk breakup, and for different kind of for these different conditions, what are the fragments that result? And this is from the study of Low and List that I mentioned earlier. Interestingly, once you start with a Marshall-Polymer distribution, the Marshall-Polymer distribution is not necessarily an equilibrium distribution, right? Because larger droplets, these different lines are different Marshall-Polymer distributions, different exponential. Larger droplets will likely break up and form. So if you have a large droplet here, it will likely break up and give rise to various smaller droplets. And some of these smaller droplets may collide and coalesce and form large droplets. So you could imagine that you could reach an equilibrium situation, right, where the two tendencies kind of balance each other out, if you will. This was studied, this kind of equilibrium distribution, if you will, studied by others, by Valdez and Young in the 80s. And they found some kind of equilibrium distribution that has different modes, peak A, peak B, and peak C. Even for different liquid water content. Okay, liquid water content is the integral over the vertical direction of density times the liquid water mixing ratio. Okay, so it's a mixture. It's a measure of how much liquid water you have in the cloud, right? As you might expect from this formula. Yeah, and so they found that even for different liquid water contents, going from 1 gram per meter cube to 8 gram per meter cubes, and spanning quite a few different rain rates, these tend to be quite similar, and you have peaks at about 2 millimeters, 1 millimeter, and 0.1 millimeter ish. And this is reached after a relatively long time, after about 1 hour, the author has observed. Okay. Okay. Now, the second thing I wanted to tell you today was about the other kind of spectrum. We know that precipitation can form as rain, could fall, as rain, but it could also fall as snow. And so, how does what does the distribution of snowflakes look like? Okay. Notice we're talking about snowflakes and not ice crystals. Snowflakes are an aggregate of all the ice crystals that have formed and that started to fall. Okay. And snowflakes are most of the precipitation that falls. Account for, most of the sort of ice precipitation that falls. Okay. Okay. Now, first of all, there's a question of how do we give an answer, right? Because for liquid droplets, things like mass, diameter, radius, they're kind of synonymous in a way, and it's kind of easy to estimate one from the other, right? Because you can always assume that with some degree of approximation for small enough droplets, these would be spherical. Large droplets would not be spherical, but small enough, you could approximate that. Snowflakes are highly irregular, as we all know. I'm assuming you've all picked up snowflakes at some point in your life, and they are highly irregular, right? They're kind of flat, and they have like weird fractal shapes. And so, how do you measure? How do you measure this size distribution? Is it in terms of the mass or what? So often data is given either in terms of the mass of the snowflake or the equivalent diameter that a liquid water droplet would have if it was melted, if it originated from the melting of that particular snowflake. Okay. Now, one of the first studies in this respect was from Goon and Marshall, and they estimated that the spectrum of snowflakes is not too different from the Marshall-Palmer distribution. Okay, and in particular, it followed sort of an exponentially decreasing form, where again you have a multiplying coefficient in front, and some parameter here that has the dimension of meter to the -1, and depends on the radius, almost like the inverse square root of the radius. Notice that unlike before, where we had n0 was a constant, okay, and here it had been estimated by the form. Here, n0 actually depends on the diameter of or the radius of on the shape of the snowflake. Okay, this is some observations that have been made from different places, different cases, and different precipitation rates. I wouldn't call them rain rates, but different precipitation rates. And again, you can see that to a good extent, there is good agreement. When the precipitation rate is high, the agreement is not quite so good for greater snowflakes. But yeah, by and large, I'd say it's not too bad. And obviously, this goes without saying. It's probably something that we're all familiar with. The fall speed of snow and rain is very different, and rain is typically faster than snowflakes. Given what we said about rainfall, can we say something like this, about aggregation, breakup for snowflakes as well? Well, first of all, as we said, dendrites, they kind of look like snow, so you might be tempted to think that dendrite snow are just dendrite ice crystals. That's not entirely true. And particularly larger snowflakes, they are made of the aggregation of different ice crystals, different dendrites and different plates that they collect as they fall. Not only that, not only collection can happen, but also the diffusional growth can also happen. So maybe, you have the snowflake, which is some dendrite that has formed. Maybe the dendrite is falling. I'm not going to be able to draw this really nicely, but is falling in an area where ice needles can grow, right? And so you're growing ice needles even more than an area where where thin plates can grow, and so you grow thin plates around, and then needles again, or prisms and whatnot. And so you end up having a very complex structure because you are accumulating ice under different forms, essentially, okay? Sometimes you can have collisions between different snowflakes or between different ice crystals, and so that adds to the complexity. But yeah. What did I want to say? Yeah. So, at a theoretical level, it's so hard to try and study snowflakes just because they are very complex structures made of a very complex material in very complex environments, and so it's kind of hard to study these processes in general. Another form of precipitation that I don't know if you are or not familiar is hail. Okay, and we should add. We'll talk about hail and then we'll conclude. We should add another category to this, which is type of precipitation called graupel. Graupel spelled. Let me write it here. Graupel spelled as GRAUPEL. And graupel is essentially formed by is formed when you have an ice crystal or a snowflake or whatever that is falling, and it falls through a region full of super cool liquid water droplets, and it accumulates a lot of these super cool liquid water droplets. Okay, so this is kind of in between hail and snow. Don't quote me on this, but it's very common in conditions like orographic rain, or when you have in sort of mid-latitude cold precipitation cases. So whenever you have mixed phase clouds generating precipitation in cold environments that doesn't just melt in larger droplets, then you can have graupel. Okay. Anyway, graupel aside, the other precipitation type that we'll talk about today is hail. Okay. Hail is formed by extreme riming, when there's a lot of riming happening within the cloud. Hailstones are typically really, really large, and they are formed. The hailstones, they can go from anywhere from 1 centimeters to 10, 15 centimeters in diameter, so really, really large. And they're produced when graupel or frozen raindrops collect super cool cloud droplets. So you have these graupel particles that are falling down Suppose that they accumulate even more um, supercooled liquid water droplets. At some point, they reach a certain radius um, that reaches a certain radius that make us classify them as hailstones. Okay. What is interesting is that unlike other forms of precipitation, the latent heat that is released in the formation of hail can actually be significant. And hailstones, because of this, can be a few degrees warmer than their surrounding environment. Actually, sometimes the latent heat that is released can cause a partial melting of some of the layers of hailstones. This can be determined sort of quantitatively. It can be determined by assuming a balance, essentially, by from two different heating rates. The first heating rate is due to the accretion of supercooled liquid droplets. Okay, and the other heating rate is the heat that is gained by sublimation. Okay. Again, no need to get too much into the specifics and the details of this, but these are the two heating rates. You can assume a balance between the two. There's also there's also heat that is lost to the air by conduction. Okay, so you have what is gained by gained by the accretion by supercooled liquid droplets, what is gained by sublimation, and this is balanced by what is lost. Okay, if you solve this equation, you can find the temperature of the hailstone. Okay, just FYI. Hailstones have very complex shapes, although they're not as complex as ice crystals, where ice crystals you can have needles and plates. Hailstones tend to be quasi-spherical, so often people just assume that hailstones are spheres. Okay, and if you do that, then you can approximate their terminal speed by this velocity, where this is the density of the ice that is deposited, the density of the air, the radius of the stone. This is some coefficient, like a drag coefficient. Typical values go from between 0.5 to 0.8. And this is the gravitational acceleration, 9.81 meters per second square. And this is the terminal velocity. Okay, notice that it increases with the square root of the radius. Notice here I wrote rho of I. The density of ice can actually depend on the conditions at which the ice is formed. So this is something that can be actually variable depending on how hail is formed. The hailstone is formed, and rate of growth of hailstones can be written in very simple formula using the fall speed and the liquid water content, which we defined earlier. This is kind of similar to the formula that we had for the growth of liquid water droplets as they fall. Okay. Finally, one interesting thing that makes this problem particularly complicated is that very often when you form hailstones, melt as they fall. Okay, this may be because, this is due to the fact that the environment, as these fall, become warmer than the environment where these formed. Suppose that you're dealing with a summer storm. Temperatures at the surface will be really, really high, and so the hailstone will melt. Now, the melting of the hailstone is by itself a really complicated process. Now, the first approximation is that the hailstone, this is true also for grapple, it is falling through the air, some melting begins. Now, if you imagine the hailstone, some outer layer begins to melt, just assume that this becomes liquid water, okay? And you can compute how the the melting proceeds. You know, if AI is the radius of the ice, how AI changes as you continue to fall, and this melting continues. However, what I wanted to show you here, the melting process we know to be much, much more complicated than just that, right? Because first of all, when you have ice and you start to melt some of the, you know, the outer layers of the ice, if you could zoom in, you'd see that this melted ice, this water, because you're falling down, it will move to the sides, right? It will move to the sides of the ice particle, and you start to have something that looks like this with this kind of ring. But also, because you're falling down, similar arguments to the instabilities that we talked about would also apply here, and you begin to shed essentially smaller droplets, okay? And so you leave behind a lot of smaller droplets. These might have an effect on the cloud, might feed back on the properties of the cloud, and you'd end up with a situation where you have a hydrometeor where the ice core is really, really small, and you have a lot of water. And this now becomes much more complicated because here you have environmental temperature, and here you have freezing temperature. So this will cause convection inside of the melting hailstone. And so this can lead to substantial consequences, and it can be very complicated to model, because if you were to include this in the model, it would be practically impossible to include all the details of this. But the details of this might actually have a measurable impact on what's going on outside in the environment and in the storm. Okay, I think this concludes what I wanted to say about rain, snow, and hail, and partially grapple. This more or less concludes the part of the class on microphysics that was based on the Rogers and Yao. Next class, we will talk about isotopes, which is still a topic that's connected to the microphysics, although it will be slightly different from what we talked about until now. As usual, if you have any kind of questions, don't be shy. Please let me know. Feel free to get in touch. And otherwise, I will see you all for the next lecture. Thank you very much for listening.